Welcome back. This is lecture 22, and in this lecture we will discuss the remaining properties of image of a subset under function. So let's discuss the remaining properties. So before that, let's try to recollect what we have seen in the previous lecture. For any subset of x, we have defined, and f is a function from x to y, we have defined image of this subset under the function f, and it is denoted as f of a, usual notation. This is not f of any point, f of a. So it's a collection of all the elements of the form f of x, or it's a collection of all the images of the elements of a. Okay, or in other words, this is same as writing an element in y such that y is equal to f of x for some x in a. So it has those elements has a pre-image only in a. Okay, and in fact we have discussed some properties under this. Today we will discuss some new properties. So let's start with. So the first property that we will be discussing here will be about the complement of the subset image of a subset of x. Okay, so first of all, if we have a set A in x, and this is y, and this is the function f. Okay, so definitely we are going to have some f of a here. Now the question is, if I talk about the complement of this a, that is this remaining part, whatever is in green in this case. So the question over here is that, does this remaining part map to the remaining part, the complement of f of a? So the question over here is that, does this green part map to the green part in the codomain for every function? This is not true in general. This is not true in general, and in fact you will prove that the equality hold, that is the image of this complementary part, is same as the y difference the image of this f of a, if and only if the given function is onto, or if and only if the given function is onto and 1 1, that is it has to be a bijection. So meanwhile we will construct that idea. So in fact we want here we will see what is the condition that is required to show that f of the image of the complement of a is same as y complement f of a, right? This is not true in general, as I mentioned. So in fact we will see one by one. So to show that this are equal, we want this y difference f of a has to be a subset of f of x difference a, and the vice versa, right? So first we will see what is the condition that is required for this to happen. Okay, so for this to happen, that means for any elements in y difference f of a should be a image of x difference a. For this to happen, you will see that the condition for f is required, that f has to be onto. So this you can actually practically see by starting with any elements, and gradually ultimately you will see that for this thing to happen, for the same element to belong to f of x difference a, you need the help of onto map. You need a map to be onto, only then you can exhibit this relation. Similarly, if you want to show that f of x difference a is a subset of y difference f of a, the condition that is required on f is that f is 1 1. Not only this, that the converse way also this is true, that is when f is onto, then this has to be true, and when f is 1 1, then this has to be true. So in this class we are going to discuss these two results. We are going to prove this two result, and ultimately the consequences would be that these two sets are equal if and only if the given function is bijection. Not even one condition, but both these conditions are required to exhibit the equality. So let's consider that as a statement, theorem. Yeah, so this is a biconditional statement. First we need to have a function, let f from x to y be a function, then f is onto if and only if y difference f of a is contained in f of x difference a for any set a in x. So if this is true for any in x and f is onto, and if f is onto, then this is true for any a in x. So we'll prove this considering one by one statement. So you're given that, first I'll prove that I'll assume the direct statement. I'll prove that this is true for any set in x. So you're given that f from x to y be onto, let a be a subset of x, any subset of x. You need to show that y difference f of a is contained in f of x difference a. So you need to start with an element over here. I'll call it as y, as it's a subset of y, and you need to show that this element belongs to f of x difference a, f of x, not here. Ultimately we are showing that this set is contained in the set mapped by x difference a. So let y be here. Okay, so here this is a subset of y, and this assures that since y is any point over here, since f is an onto, that assures that there has to be a point in the domain which acts as the pre-image of this y. So therefore there exists x in a such that y is equal to f of x. Okay, now we need to show that this y is in f of x difference a. Sorry, this is not a, this is x. X in as of now we don't know from where that x is coming. So x belongs to x such that y is equal to f of x. Okay, so now if I can show that this x is not in a, that is, if this is a, then if x, actually the pre-image for this y is coming from this part, okay, that is this part, then I am done. So if x belongs to that part, then definitely f of x has to come from f of x difference a. Okay, so we need to show that this x which is coming from this x is not in the set a. Okay, so I'll write down. So this is true as f is onto. We need to show that we need to prove that x is not in a, and therefore x should come from x difference a, which from which we can immediately conclude that f of x come from f of x difference a, that is y comes from f of x difference a. And this is not difficult to show. You try proving it using contradiction. So if x is in a, then this would immediately implies that f of x belongs to f of a, right, which would be same as saying y belongs to f of a. But by the definition, by the star, we know that y is coming from y but not from f of a. So this contradicts to our assumption, contradicts to star, and therefore this in fact contradicts to the fact that y is not coming from. This implies that y does not belongs to f of a. It is from y, but it's not from y is coming from y, but it's not coming from f of a. So therefore this from this contradiction we can arrive to the conclusion that x is not in a, and therefore x should be a point coming from x but not a, and this implies that f of x belongs to f of x difference a, that is y belongs to f of x difference a. And therefore we have proved that y difference f of a is contained in f of x difference a. So this is the first part. Conversely, if I assume that this is true, let's assume that y difference f of a is contained in f of x difference a. We need to show that f is onto. So basically, to show that f is onto, it's enough to show that the range of the entire function, that is image of the entire set f of x is equal to y. This, if I prove this, then we are done, because that's again a biconditional statement. Okay, and that we need to prove from here. This is true for any. So you are given this. So in fact, for a particular choice of a, if you can exhibit this relation, then you are done. Okay, now that's clear from here. If you choose that a to be an empty set, then definitely f of a will be an empty, and therefore y difference f of empty will be nothing but y. So that will be your right hand side, and in fact your left hand side is going to be f of x difference empty, which is going to be simply f of x, and therefore you will have one relation, that is y is contained in f of x. But you already know that f of x, since it's an image subset of a certain set, it has to be in the codomain. It's always contained in y, so that relation is always true, and then therefore we are done. Okay, so let a be an empty set which is a subset of x, and from our assumption, thus from assumption we have y difference f of empty set is contained in f of x difference empty, which is same as saying y difference empty, because f of empty is empty, and this is same as f of x, because x difference empty is f of x. That is same as saying y contained in f of x. And so this is always true, and sorry, this is what we have proved. And also f of x contained in y from the definition. Thus using 1 and 2, you will see that y is equal to f of x, that is the range of the function f, and therefore f is onto. So this proves the first result, and a very dual statement that we have, analogous statement, in fact a dual statement to this statement is this what we have already mentioned outline, that is x difference a, or the image of x difference a is contained in y difference f of a if and only if the function f is 1 1. So that's the next theorem. Let f from x to y be a map, then f is 1 1 if and only if f of x difference a is contained in y difference f of a for any subset a of x. Okay, so the proof for this is again similar. So let we first assume that function is 1 1, and we prove that f of x difference a is contained in y difference f of a. Okay, so let's start with an element in f of x difference a. So if y belongs to f of x difference a, by definition there should be a pre-image for this y in x difference a, okay. So that is, suppose this is your a, then there is a pre-image x which acts as the pre-image for y. Okay, so therefore there exists x in x difference a such that y is equal to f of x. Okay, so definitely this y belongs to f of x difference a. This is by the definition of image subset. Now you need to show that this y, definitely this y is coming from y, but to be more precise you need to show that this y is not in f of a. Okay, then you are done. So we need to prove y do not belongs to f of a. So what will happen if y belongs to f of a? If y belongs to f of a, then there exists x in a such that y is equal to f of x. Okay, I'll use the other notation because I've used x over here, so I'll call this as x1, this as x1. Okay, but you know that y, therefore you also know that y is equal to f of x, and x is coming from x difference a, and here, so now it's time to use the fact that the function f is 1 1. So you have f of x is equal to x1 here, so this would imply that x is equal to x1, and this immediately says that because x1 belongs to a, this immediately says that x belongs to a. That contradicts to what we have assumed. You are saying that x is in x difference a, so x is not a point from a, and that's contradiction to the start. Why we are having this contradiction? Because you are assuming that assuming that y belongs to f of a, and therefore we need to have y is not in f of a. Okay, now the converse part is again similar to how we have produced a proof for the previous result, because we are going to fix one particular a to get this. So we assume that f of x difference a is contained in y difference f of a for any subset of x. Fine. So we need to show that f is 1 1. So this basically I'll show using the definition. that is, I'll show that if x1 is not equal to x2, then f of x1 will not be equal to f of x2. So I have one choice of a. So what I'll do is that I'll choose a singleton a. So let x1 belongs to x. So if x1 belongs to x, I'll call a to be a singleton x, which is a subset of x, and thus by our assumption we should have f of x difference x1, singleton x1, is contained in y difference f of singleton x1. Okay, and therefore if I take any element from x other than x1, then it's not going to be its image is not going to be not going to fall, it's not going to be equal to f of x1, because image is always a point in y, but this assures that it's not going to f of x1, it's going to fall in any other image of a subset other than f of singleton x1. Okay, so hence it is clear from here, for every x in x such that x is not coming from x difference x1, that is same as saying x is not equal to x1, this would implies that f of x will never equal to f of x1. So in fact, in general, we have proved this by fixing one element and varying every other element in x which is not same as x1. Okay, so thus by definition f is 1 1. Okay, now combining these two results, we have a result wherein the equality attained, and that is true for a function which is bijection. So theorem, let f from x to y yeah, in fact I can say in this way, a function f from x to y is bijection. So this can be considered as one definition of a bijection, because it's a if and only if statement. If and only if f of x difference a is same as y difference f of a for any subset of x. Okay, the proof is combination of the previous two proof. So with this I wind up this session. I hope you have liked this video. If yes, then please hit a like button to motivate me for the further videos, and stay tuned for the next class that will be on inverse image of a subset under function. Thank you for watching this.